Today I will study the driven pendulum. The final result will be this workspace you see here. The workspace delivers the equation of motion for the driven pendulum. It is a differential equation according to Newton's second law. But let's start with a clear workspace. We start by creating a function called path of free particle. Newton's first law states that in some inertial frame of reference, an object continues to move in space at a constant velocity. This movement takes time, so our function depends on time. It returns a vector of two elements because we choose our path to live in two dimensions. The kinetic energy is half the mass times velocity squared. If we set the mass to 2 kg, the formula becomes simpler. We know that the velocity of our free particle is constant. In the x direction, it is 5 meters per second. But notice that the velocity here could be any function in space and time. Now for the Lagrangian function. For our free particle, the Lagrangian is just the kinetic energy. In general, a Lagrangian does not only depend on the velocity, but also on time and position. We are not using time and position here, but they nevertheless have to appear in the input vector. The Lagrangian equations are differential equations. They are constructed out of the Lagrangian function. The differential equations are applied to some path function. Here we use our specific path of a free particle. The result in general is a function of time. We set the time to 10 seconds here. But if the path we fed into the equations is a viable physical path, the result should be a very special function. It should be the zero vector. So let's print the result. We indeed see the correct result at the bottom, but the real power of the system only shows when I replace the specific path of a free particle. I create a vector of two arbitrary functions. Call them qx and qy. Then I do the replacement of the specific path with the arbitrary path. After running the workspace again, we see the general equations of motions for the free particle. I want to make the equations prettier. First I replace 10 by some time t. Second, I introduce the mass m into the kinetic energy. The specific path can be thrown away, it is not needed anymore. After running, we see Newton's equations of motion for the two-dimensional free particle in their standard form. Now we model a particle in the gravitational field by introducing the potential energy. It depends on the height of the particle above ground. It is m times g times the height, where g is 9.8 meters per second, the acceleration due to the gravity of the Earth. The Lagrangian is kinetic energy minus potential energy. And the Lagrangian now depends on the height. Run the workspace and Newton's equations for the particle in the homogeneous gravitational field are delivered. To get the equations for the pendulum, we introduce a transformation of the coordinates. The new single coordinate is the angle between the rod and its position at rest. So the old coordinates become dependent on each other. The horizontal position x of the bob is L times sine of the angle, where L is the length of the pendulum. The height of the bob is h minus L times cosine of the angle. H is the height of the pivot. The Lagrangian of the pendulum is obtained by prepending the transformation. In this function composition, the Lagrangian of the independently moving particle is reused completely unchanged. The new Lagrangian equations are now applied to some function phi. We can do the functional replacements now. Running the workbook delivers the equations for the pendulum. In the last step, I introduce the function height of pivot as a driver to the pendulum. It is an arbitrary function of time. The replacement is easily done, but notice that the transformation of coordinates now becomes time dependent, and with this the Lagrangian becomes time dependent in an explicit manner. Running the workspace yields the equation for the driven pendulum. Thanks for watching.